Have you ever wondered if everything we think we know about our place in the universe might be completely wrong? What if the very ground beneath your feet, the solar system we call home, and every star you see twinkling in the night sky exists within something so vast and so empty that it challenges everything scientists have believed about the cosmos for decades? Tonight, we're diving into one of the most extraordinary discoveries in modern astronomy. A revelation so profound that it could rewrite our understanding of space, time, and the fundamental structure of reality itself. Scientists have found evidence that Earth and our entire galaxy might be trapped inside a colossal cosmic void, a bubble of near-emptiness stretching 2 billion light-years across. And the most incredible part, the proof comes from echoes of the Big Bang itself, ancient whispers from the birth of the universe that have been traveling through space for nearly 14 billion years. This isn't science fiction. This is cutting-edge research that emerged just months ago, presented at the Royal Astronomical Society's National Astronomy meeting. And if these findings hold up, they could solve one of the most perplexing mysteries plaguing modern cosmology, while simultaneously forcing us to question whether our cosmic neighborhood is as ordinary as we've always assumed. But before we explore this mind-bending possibility, let me share something that might surprise you. The idea that we might live in an unusual part of the universe actually emerged from a crisis so severe that it's been keeping cosmologists awake at night for over a decade. They call it the Hubble tension, and it represents a fundamental breakdown in our understanding of how fast the universe is expanding. Picture this scenario. You have two incredibly precise measuring tools, both designed to calculate the same thing: the expansion rate of the universe itself. One tool looks at the cosmic microwave background, that faint afterglow of the Big Bang that bathes the entire cosmos in ancient radiation. This method gives us an expansion rate of about 67 kilometers per second per megaparsec. The other tool uses nearby pulsating stars, called Cepheid variables, to measure cosmic distances. This method consistently returns a value of 73.2 kilometers per second per megaparsec. Now, a difference of 6 units might not sound like much, but in the precise world of cosmology, it's absolutely massive. It's like having two perfectly calibrated rulers that give you completely different measurements for the same object. One of them has to be wrong, or there's something fundamentally broken about our understanding of the universe itself. For years, scientists hoped this discrepancy would disappear as measurements became more precise. Instead, the opposite happened. The more accurately they measured, the more pronounced the disagreement became. Multiple independent research teams using completely different methods kept finding the same troubling result. The universe appeared to be expanding at different rates, depending on where you looked and how you measured it. This is where our story takes a fascinating turn, because sometimes the most revolutionary solutions come from the most unexpected places. Dr. Indranil Banik, an astronomer at the University of Portsmouth, had been thinking about this problem from a completely different angle. What if the issue wasn't with our measurements at all? What if the problem was with our assumptions about where we live? You see, modern cosmology has been built on a foundational principle called the cosmological principle. This principle assumes that on large scales, the universe is homogeneous and isotropic. In simpler terms, it assumes that matter is distributed roughly evenly throughout space, and that there are no special or preferred locations. Our cosmic neighborhood should be pretty typical, no different from any other region of space billions of light years away. But what if that assumption is wrong? What if our galaxy, our local group of galaxies, and everything within billions of light years of Earth exists within a cosmic anomaly. A region so unusual that it skews every measurement we make about the broader universe. This is where the concept of the cosmic void enters our story. Imagine space as a vast ocean, and galaxies as islands scattered across its surface. In most regions, these islands are distributed relatively evenly, but occasionally you might find enormous stretches of nearly empty water where islands are few and far between. In cosmology, these empty regions are called voids, and they represent some of the largest structures in the known universe. The particular void that Dr. Bannock and his colleagues have been studying isn't just any ordinary empty region of space. They call it the KBC void, named after the astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who first studied it extensively in 2013. This cosmic bubble of emptiness spans approximately 2 billion light-years in diameter, making it one of the largest coherent structures ever identified in the observable universe. To put that scale into perspective, light traveling at 300 million meters per second would take 2 billion years to cross from one side of this void to the other. Within this incomprehensibly vast region, the average density of matter is about 20% lower than what we observe in typical regions of the universe. It's not completely empty, mind you. It contains our Milky Way galaxy, our local group of neighboring galaxies, and the larger structure known as the Laniakea supercluster. But compared to the cosmic average, it's remarkably sparse. The truly remarkable thing is that our galaxy appears to be located very close to the center of this enormous void. Not on the edge, not in some random location within it, but right near the middle. This positioning is crucial because it means that nearly everything we can observe in the nearby universe is also within this underdense region. Now, you might be wondering how scientists could possibly detect something so vast and subtle. After all, empty space looks pretty much the same whether you're in a void or in a typical region of the universe. The answer lies in those echoes from the Big Bang I mentioned earlier. These cosmic fossils are called baryon acoustic oscillations, and they represent some of the most ancient and fundamental signatures we can observe in the universe today. Let me paint you a picture of what happened in the early universe to create these cosmic echoes. Imagine the universe when it was only a few 100,000 years old. At this time, space was filled with an incredibly hot, dense plasma composed of protons, electrons, and photons, all interacting intensely with each other. Within this primordial soup, tiny density fluctuations began to grow under the influence of gravity. Picture an overdense region within this cosmic plasma. Gravity tries to pull more matter toward this region, making it even denser. But the intense heat and radiation pressure push outward, resisting this gravitational collapse. These competing forces create something remarkable. Spherical pressure waves, essentially sound waves, that propagate outward through the plasma at about 1/3 the speed of light. These cosmic sound waves traveled for approximately 400,000 years before something crucial happened. The universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This event, called recombination, suddenly made the universe transparent to light for the first time. The photons that had been trapped in the plasma were finally free to travel through space. But more importantly for our story, the sound waves that had been propagating through the plasma suddenly froze in place. These frozen sound waves became permanent features in the cosmic landscape. The regions where the waves had pushed matter together became slightly denser than average, while the regions they had evacuated became slightly less dense. Over billions of years, these tiny density variations served as the seeds for all the large-scale structure we see in the universe today. galaxies preferentially formed in the denser regions, creating a subtle but detectable pattern in their distribution. The beautiful thing about baryon acoustic oscillations is that they provide a standard ruler for measuring cosmic distances. Just as the wavelength of a musical note tells you about the instrument that produced it, the characteristic scale of these cosmic sound waves tells us about the conditions in the early universe. More importantly, because we understand the physics involved so precisely, we can predict exactly what this scale should look like at any point in cosmic history. This is where Dr. Bannock's detective work becomes truly fascinating. By carefully analyzing more than 20 years of observational data on baryon acoustic oscillations, his team found something unexpected. The pattern of these cosmic sound waves in our local region of the universe appeared subtly distorted compared to what they should look like if we lived in a typical cosmic environment. The distortion is exactly what you would expect if our measurements were being influenced by our position within a large cosmic void. You see, voids aren't just empty regions of space. They're dynamic structures that influence the motion of everything around them. Matter naturally flows away from underdense regions toward denser areas, creating large-scale velocity fields that can affect how we measure distances and expansion rates. Think of it like this. If you're standing in a river, the water around you is flowing downstream. If you try to measure how fast a leaf is moving relative to the riverbank, you need to account for the current. Similarly, if our galaxy is embedded within a cosmic void, all the nearby galaxies we use to measure the expansion rate of the universe are also influenced by the outflow of matter from this underdense region. This outflow creates additional apparent recession velocities on top of the normal cosmic expansion. When we measure the distance to nearby galaxies using their redshift, we're actually measuring this combined motion. The result is that local measurements of the Hubble constant appear artificially high compared to measurements based on the cosmic microwave background, which reflects conditions in the early universe before these local peculiar motions developed. The statistical evidence for this void model is remarkably strong. Dr. Bannock's team found that their data supports the existence of a local void with odds of about 100 million to 1 compared to a void-free model. In the language of statistics, this represents overwhelming evidence that something unusual is happening in our cosmic neighborhood. But the implications extend far beyond just solving the Hubble tension. If confirmed, this discovery would fundamentally challenge one of the basic assumptions of modern cosmology, the cosmological principle, which assumes that our location in the universe is typical and unremarkable, would need serious revision. We would have to accept that Earth and everything we can observe exists within a cosmic anomaly, a region so unusual that it affects every measurement we make about the broader universe. This raises profound questions about how such enormous voids could form within the framework of our current understanding of cosmic evolution. The standard lambda cold dark matter model, which has successfully explained many features of the universe, struggles to account for structures as large and empty as the KBC void. Some researchers argue that voids this size simply shouldn't exist, according to our current theories of how cosmic structure forms and evolves. The controversy extends to the very foundations of our understanding of gravity and dark matter. Alternative theories of gravity, such as modified Newtonian dynamics, naturally predict enhanced structure formation on large scales, potentially explaining how such massive voids could develop. These theories also make different predictions about galaxy motions and cosmic expansion rates, offering testable alternatives to the dark matter paradigm that has dominated cosmology for decades. Recent observations have provided additional support for unusual large-scale motions in our cosmic region. Data from the Cosmic Flows 4 galaxy catalogue reveals bulk flows of galaxies exceeding 400 kilometers per second over scales of 300 million light-years. These coherent streaming motions are larger than predicted by standard cosmological models, but align well with expectations for matter flowing out of a large cosmic void. The evidence continues to accumulate from multiple independent sources and observational techniques. Studies across the entire electromagnetic spectrum, from radio waves to X-rays, consistently suggest that we live in a region with below-average matter density. Galaxy counts, measurements of cosmic background radiation, observations of distant supernova, and studies of galaxy peculiar velocities all point toward the same remarkable conclusion. As we stand on the threshold of this potential paradigm shift in our understanding of the cosmos, we must grapple with the implications of living in such an unusual cosmic environment. The universe may be far stranger and more varied than we ever imagined, with vast regions of emptiness punctuated by dense cosmic metropolises. Our cosmic address may not be typical suburban space, but rather the equivalent of living in a cosmic wilderness, billions of light years from the nearest major concentration of galaxies and dark matter. Yet even as this extraordinary possibility takes shape before our eyes, the true mystery deepens when we consider what this cosmic void means for our understanding of time itself. You see, living within such an enormous underdense region doesn't just affect how we measure distances to nearby galaxies. It fundamentally alters our perception of cosmic history and the very age of the universe. When astronomers look out into space, they're simultaneously looking back in time. The light from distant galaxies has taken millions, billions, even nearly 14 billion years to reach our telescopes. This means we're seeing those galaxies not as they are today, but as they were when that light first began its journey toward Earth. It's like having a time machine that allows us to witness the universe's evolution from its earliest moments to the present day. But here's where the void hypothesis introduces a fascinating wrinkle in this cosmic time travel. If we're truly embedded within this enormous bubble of emptiness, then our observations of distant cosmic history are being filtered through billions of light years of underdense space. The light from ancient galaxies, supernovae, and other cosmic phenomena has spent its entire journey traveling through a region where matter density is 20% below the cosmic average. This might seem like a subtle effect, but in the precise world of cosmology, even small systematic influences can have profound consequences. The gravitational effects of the void, the peculiar motions of galaxies within it, and the overall geometry of space-time in underdense regions all conspire to create systematic biases in our cosmic measurements. Dr. Bannock and his colleagues have been working to understand exactly how these effects might influence our estimates of fundamental cosmic parameters. The Hubble constant, which measures the current expansion rate of the universe, is just one piece of a larger puzzle. Other crucial measurements include the matter density of the universe, the strength of dark energy, and even the total age of the cosmos itself. Current estimates place the age of the universe at approximately 13.8 billion years, based on detailed analysis of the cosmic microwave background and our understanding of cosmic expansion history. But this calculation assumes that our measurements are representative of the universe as a whole. If we're actually observing from within a cosmic anomaly, these estimates might require significant revision. The implications become even more intriguing when we consider what this means for our search for life elsewhere in the universe. Cosmic voids aren't just empty regions of space. They're environments where galaxy formation, star formation, and the chemical evolution of matter all proceed differently than in typical cosmic regions. Within the sparse environment of a cosmic void, galaxies form more slowly and experience fewer gravitational interactions with their neighbors. The rate of star formation is generally lower, which means fewer heavy elements are produced and dispersed into the interstellar medium. the overall density of potentially habitable worlds might be significantly reduced compared to denser regions of the universe. Yet there's another side to this cosmic coin. Voids are also quieter, more stable environments. Galaxies within voids are less likely to experience violent mergers or close encounters that could disrupt planetary systems. The lower density of matter also means less cosmic radiation and fewer catastrophic events that might threaten the development of complex life. Could it be that our location within this cosmic wilderness has actually been beneficial for the emergence and evolution of life on Earth? Are we living in a cosmic safe haven, protected by billions of light years of empty space from the more violent and chaotic processes that characterize denser regions of the universe? These questions take on new urgency when we consider recent developments in our understanding of cosmic structure formation. Advanced computer simulations of cosmic evolution have revealed that the universe's large-scale structure is even more complex and varied than previously imagined. Vast cosmic webs of dark matter filaments connect dense nodes where galaxy clusters form, while enormous voids occupy the spaces between these cosmic highways. The KBC void appears to be one of the largest such structures ever identified, but it may not be unique. Other research groups have identified additional supervoids in different regions of the observable universe, suggesting that such enormous underdense regions might be more common than standard cosmological models predict. This raises profound questions about the fundamental assumptions underlying our current understanding of cosmic evolution. The lambda cold dark matter model, which has been the standard framework for cosmology for over 2 decades, was developed based on observations that now appear to have been systematically biased by our unusual cosmic location. If the void hypothesis is correct, we may need to develop entirely new theoretical frameworks to understand how the universe actually works. The formation of such enormous underdense regions requires specific conditions in the early universe that aren't easily explained by current models. The physics of how matter flows out of these voids over cosmic timescales involves complex interactions between ordinary matter, dark matter, and dark energy that we're only beginning to understand. Some researchers have suggested that the existence of supervoids like the KBC void might actually provide evidence for alternative theories of gravity. Modified Newtonian dynamics, or MOND, naturally predicts enhanced structure formation on large scales, potentially explaining how such massive voids could develop within the age of the universe. These alternative gravity theories also make different predictions about how matter should behave within and around cosmic voids. Unlike dark matter models, which predict specific patterns of galaxy velocities and clustering, modified gravity theories suggest that the apparent effects we attribute to dark matter might actually arise from our incomplete understanding of gravitational physics itself. The debate between dark matter and modified gravity theories has been simmering in the cosmological community for decades. But the void hypothesis adds a new dimension to this fundamental question. If our local cosmic environment is genuinely unusual, it becomes much more difficult to test these competing theories using observations of nearby galaxies and cosmic structures. Recent advances in observational astronomy are beginning to provide the tools needed to resolve these deep questions about our cosmic environment. The James Webb Space Telescope, with its unprecedented ability to observe distant galaxies and cosmic structures, is already revealing surprising details about the early universe that challenge existing models. Next-generation galaxy surveys, such as the Vera Rubin Observatory's Legacy Survey of Space and Time, will map billions of galaxies across cosmic history, providing the statistical power needed to definitively test the void hypothesis. These surveys will measure galaxy positions, distances, and velocities with unprecedented precision. allowing astronomers to map the three-dimensional structure of cosmic voids and filaments across billions of light years. Perhaps most importantly, these future observations will extend far beyond the boundaries of the proposed KBC void, allowing us to test whether cosmic expansion rates and other fundamental parameters return to expected values in more typical regions of the universe. If the void hypothesis is correct, we should see systematic differences in cosmic measurements between our local underdense region and the denser cosmic environment beyond. The gravitational wave astronomy revolution, pioneered by facilities like LIGO and Virgo, offers yet another window into our cosmic environment. Gravitational waves from merging black holes and neutron stars propagate through space at the speed of light, carrying information about the cosmic structures they encounter along their billion-year journeys in space-time itself, provide a completely new example to Earth. These RIP-independent way to probe the matter distribution between us and distant cosmic events. If we're truly embedded within a large, underdense region, the gravitational wave signals should show subtle signatures of their passage through this cosmic wilderness. The accumulating evidence from multiple independent observational techniques creates a compelling case for reconsidering our cosmic address. Galaxy counts, peculiar velocity measurements, gravitational lensing studies, and now baryon acoustic oscillation analyses all point toward the same remarkable conclusion. We appear to live in a cosmic anomaly, a region so unusual that it has shaped every astronomical observation humans have ever made. This realization forces us to confront fundamental questions about the nature of scientific inference itself. How can we study the universe objectively when every measurement we make is potentially biased by our unusual cosmic location? How do we separate local effects from universal principles when our only laboratory is embedded within a cosmic anomaly? These epistemological challenges echo similar problems that have arisen throughout the history of science. Galileo had to account for Earth's motion when making astronomical observations. Einstein had to consider the observer's reference frame when developing relativity theory. Now, modern cosmologists must grapple with the possibility that our cosmic reference frame itself is highly atypical. The void hypothesis also raises intriguing questions about the anthropic principle and the apparent fine-tuning of physical constants that allow complex structures like galaxies, stars, and planets to form. If cosmic conditions vary significantly between different regions of the universe, perhaps the apparent fine-tuning we observe is simply a selection effect. We find ourselves in a region where conditions happen to be suitable for the emergence of observers like ourselves. Yet even as we contemplate these profound implications, the scientific process continues to unfold with characteristic rigor and skepticism. Independent research groups around the world are working to verify, challenge, and extend the void hypothesis using different datasets and methodologies. Some studies have found evidence supporting the existence of large-scale underdensities in our cosmic neighborhood, while others have questioned whether such enormous voids are consistent with our current understanding of cosmic structure formation. The scientific community remains divided on the interpretation of the evidence, as is appropriate for such a potentially revolutionary discovery. The debate continues to evolve as new observations become available and theoretical models become more sophisticated. Computer simulations of cosmic structure formation are being refined to better understand how large voids form and evolve over cosmic time. Observational programs are being designed to test specific predictions of the void hypothesis against alternative explanations for the Hubble tension and other cosmological puzzles. What makes this scientific detective story even more compelling is the elegant way that seemingly unrelated cosmic mysteries begin to connect once we accept the possibility that we're living in this vast underdense region. The void hypothesis doesn't just address the Hubble tension. It potentially explains a constellation of puzzling observations that have been accumulating in the astronomical literature for decades. Consider, for instance, the peculiar behavior of our own galaxy's motion through space. The Milky Way is racing through the cosmic web at approximately 627 kilometers per second relative to the cosmic microwave background. This might sound fast, but it's actually surprisingly slow compared to what we observe for other galaxies in similar cosmic environments. Most galaxies show much higher peculiar velocities as they're pulled around by the gravitational influence of nearby massive structures. Our galaxy's relatively sedate motion through space has long puzzled astronomers. But if we're located near the center of an enormous cosmic void, this leisurely pace makes perfect sense. There simply isn't enough nearby matter to gravitationally accelerate our galaxy to the extreme velocities we see elsewhere in the universe. We're coasting through a cosmic desert where the gravitational landscape is remarkably flat and gentle. This realization connects to another long-standing puzzle in cosmology known as the local group timing problem. Our galaxy and the nearby Andromeda galaxy are currently approaching each other and will likely collide in about 4 billion years. But when astronomers try to model the orbital dynamics of this local galaxy pair, they find that the timing doesn't quite work out according to standard cosmological models. The problem is that there doesn't appear to be enough matter in our immediate cosmic neighborhood to account for the gravitational binding of the local group. Either there's missing dark matter that we haven't detected, or the dynamics of galaxy interactions work differently than we think. But if we're embedded within a large underdense region, the reduced matter density naturally explains why local gravitational dynamics appear anomalous compared to theoretical predictions. The void hypothesis also sheds new light on observations of the cosmic web itself. When astronomers map the large-scale structure of the universe, they see a complex network of filaments and nodes where galaxies cluster together, separated by vast, empty regions. But our local cosmic neighborhood appears to be remarkably smooth and featureless compared to these distant cosmic metropolises. This smoothness extends to the cosmic microwave background radiation itself. When we look at the temperature fluctuations in this ancient light, we find that our local sky is unusually uniform. There are fewer hot and cold spots than we would expect based on the cosmic average. This phenomenon, known as the cosmic microwave background cold spot, has been another persistent puzzle in cosmology. If we're viewing the cosmic microwave background from within a large void, this apparent smoothness becomes much easier to understand. The reduced matter density along our line of sight to the last scattering surface would naturally create the appearance of a colder, more uniform region in the ancient cosmic glow. What appeared to be an anomaly in the cosmic microwave background might actually be a natural consequence of our unusual cosmic address. The implications ripple outward to affect our understanding of cosmic structure formation itself. The current theoretical framework suggests that the universe began in an almost perfectly smooth state, with tiny quantum fluctuations serving as the seeds for all subsequent structure formation. Over billions of years, these microscopic variations grew under the influence of gravity to become the galaxies, clusters, and superclusters we observe today. But this story of gradual structure formation has always struggled to explain the existence of extremely large-scale structures like the KBC void. According to standard models, it should be nearly impossible for such enormous underdense regions to form within the age of the universe. The gravitational forces simply haven't had enough time to evacuate matter from such vast volumes of space. This is where alternative theories of cosmic evolution begin to look more attractive. Some cosmologists have proposed that the early universe experienced multiple phases of rapid expansion, not just the single inflationary epoch that's part of the standard model. These extended inflation scenarios could naturally produce larger scale structures than conventional models predict. Other researchers have suggested that the dark energy that drives the current acceleration of cosmic expansion might not be constant over time. If dark energy has evolved or fluctuated throughout cosmic history, it could have influenced structure formation in ways that standard models don't account for. Regions that experienced slightly different dark energy densities in the past might have evolved into the supervoids and superclusters we observe today. The most radical possibility is that our understanding of gravity itself needs revision on cosmic scales. Modified gravity theories like MOND naturally predict enhanced structure formation compared to dark matter models. In these frameworks, the apparent effects we attribute to dark matter actually arise from our incomplete understanding of how gravity behaves when accelerations become extremely small. These theories make specific, testable predictions about how matter should behave within and around cosmic voids. Unlike dark matter models, which require the existence of exotic particles that have never been directly detected, modified gravity theories propose changes to the fundamental laws of physics that govern all matter and energy. The observational tests of these competing ideas are becoming increasingly sophisticated. Astronomers are now able to measure the three-dimensional positions and velocities of millions of galaxies, creating detailed maps of how matter flows through the cosmic web. These observations reveal complex patterns of streaming motions that extend across hundreds of millions of light years. Recent analysis of galaxy velocity data has revealed bulk flows that exceed what standard cosmological models predict. Entire regions of the universe appear to be streaming in coherent directions at speeds of several hundred kilometers per second. These large-scale motions could be the signature of matter flowing out of enormous voids like the one we may inhabit. The velocity patterns also provide crucial tests of different theories of gravity and dark matter. Each theoretical framework makes distinct predictions about how galaxies should move in response to the underlying matter distribution. By comparing these predictions with increasingly precise observations, astronomers can begin to distinguish between competing explanations for cosmic structure formation. But perhaps the most profound implication of the void hypothesis concerns the fundamental question of cosmic representativeness. If our observations are systematically biased by our location within a cosmic anomaly, how can we ever hope to understand the universe as a whole? This challenge goes to the heart of the scientific method itself. Throughout the history of astronomy, we've repeatedly discovered that Earth occupies no special place in the cosmic order. We're not at the center of the solar system. Our sun is not at the center of the galaxy, and our galaxy is not at the center of the universe. This principle of cosmic mediocrity has been a guiding assumption in cosmology for over a century. But the void hypothesis suggests that while we may not be at the center of anything in particular, we may indeed occupy a highly unusual cosmic environment. This doesn't violate the principle of cosmic mediocrity in any absolute sense. After all, if supervoids like the KBC void are natural consequences of cosmic structure formation, then some observers must necessarily find themselves in such environments. The question becomes whether observers like ourselves are more likely to emerge in typical cosmic environments or in unusual ones. Dense regions of the universe experience more frequent galaxy mergers, higher rates of star formation, and more intense radiation environments. All of these factors could potentially be harmful to the development of complex life. Conversely, the quiet, stable environment within a cosmic void might actually be more conducive to the emergence of intelligent observers. Planetary systems can evolve undisturbed by cosmic catastrophes for billions of years. The lower background radiation levels reduce the risk of mass extinctions caused by cosmic ray bombardment or gamma-ray bursts from distant stellar explosions. This anthropic perspective on cosmic voids opens up fascinating new avenues for thinking about the distribution of life in the universe. Rather than focusing our search for extraterrestrial intelligence on the dense cosmic cities where most stars and planets reside, perhaps we should be looking in the cosmic suburbs and wilderness areas where conditions might be more favorable for long-term biological evolution. The void hypothesis also has profound implications for our estimates of how common life might be in the universe overall. If most potentially habitable worlds exist in dense cosmic environments where catastrophic events are more frequent, the actual probability of complex life developing might be much lower than optimistic estimates suggest. On the other hand, if cosmic voids provide safe havens where life can develop and thrive over cosmic timescales, there might be entire populations of civilizations throughout these scattered underdense regions, too far from the galactic mainstream to be easily detected by conventional search strategies. These speculations remain highly theoretical, but they illustrate how the void hypothesis forces us to reconsider fundamental assumptions about our place in the cosmic order. The universe may be far more varied and complex than we've imagined, with different regions offering vastly different environments for the development of stars, planets, and life itself. As observational technology continues to advance, we're gaining unprecedented ability to test these ideas against reality. The next generation of extremely large telescopes will be able to detect and study individual galaxies at distances that would allow us to map cosmic structure well beyond the boundaries of any local void. Space-based observatories like the proposed Nancy Grace Roman Space Telescope will survey billions of galaxies across cosmic history, providing the statistical power needed to definitively characterize our cosmic environment. These observations will reveal whether the patterns we see in our local cosmic neighborhood are truly anomalous or represent normal variations in cosmic structure. Perhaps most excitingly, advances in gravitational wave astronomy are opening entirely new windows into cosmic structure. As detectors become more sensitive, they'll be able to observe gravitational waves from increasingly distant and ancient cosmic events. These observations will provide completely independent probes of the matter distribution between us and the most distant reaches of the observable universe. The accumulating evidence from multiple observational approaches is painting an increasingly detailed picture of our cosmic environment. Each new measurement adds another piece to a puzzle that may fundamentally reshape our understanding of the universe and our place within it. Yet even as we stand on the threshold of these revolutionary discoveries, the true implications of living within a cosmic void may extend far beyond anything we've yet imagined. The void hypothesis doesn't just challenge our understanding of cosmic structure and expansion rates. It forces us to reconsider the very nature of cosmic time and the evolution of the universe itself. When we peer deep into space with our most powerful telescopes, we're essentially looking back through cosmic history. The most distant galaxies we can observe appear as they were when the universe was only a few 100 million years old, still in its cosmic infancy. These ancient galaxies are our primary window into understanding how cosmic structure formed and evolved over billions of years. But if we're embedded within a large underdense region, our view of cosmic history is necessarily filtered through this unusual environment. The light from those ancient galaxies has spent its entire journey traveling through space that may have very different properties from the cosmic average. This raises profound questions about how representative our observations of cosmic evolution actually are. The galaxies we see forming in the early universe, the rates of star formation we measure, and the chemical evolution of cosmic matter we infer from distant observations all may be systematically biased by our location within a cosmic anomaly. The challenge becomes even more complex when we consider that cosmic voids themselves evolve over time. The KBC void we inhabit today may have had very different properties billions of years ago when the light from distant galaxies first began its journey toward Earth. The underdense region may have been smaller, denser, or structured differently in the past. Understanding this temporal evolution of cosmic voids requires sophisticated computer simulations that can model the complex interplay between ordinary matter, and dark energy over cosmic timescales. These simulations suggest that voids do indeed grow and evolve significantly over billions of years, becoming larger and emptier as matter continues to flow toward denser regions. This evolutionary perspective adds yet another layer of complexity to interpreting our cosmic observations. Not only must we account for our current unusual location, but we must also consider how this location has changed over the cosmic time periods relevant to the observations we're trying to understand. The implications extend to some of the most fundamental questions in cosmology, including the nature of dark energy itself. Current observations suggest that dark energy makes up approximately 68% of the universe's total energy content and is responsible for driving the accelerated expansion of space. But these estimates are based on measurements that may be systematically affected by our location within a cosmic void. If the void hypothesis is correct, our local measurements of cosmic acceleration may not be representative of the universe as a whole. The apparent acceleration we observe could be partially due to the local effects of matter flowing out of our underdense region, rather than purely the result of dark energy acting uniformly throughout space. This possibility has led some researchers to propose that dark energy might not be a fundamental property of empty space, but rather an apparent effect that emerges from our unusual observational perspective. In this view, the universe as a whole might not be accelerating at all, and what we interpret as dark energy could actually be a consequence of large-scale inhomogeneities in the cosmic matter distribution. Such a radical reinterpretation of dark energy would have profound consequences for our understanding of fundamental physics. Dark energy has been one of the most mysterious components of the universe, requiring either exotic new forms of matter and energy or modifications to our understanding of gravity and space-time itself. If dark energy turns out to be an observational artifact rather than a fundamental aspect of cosmic evolution, it would eliminate one of the greatest mysteries in modern physics, while simultaneously creating new puzzles about the true nature of cosmic expansion and structure formation. The scientific community remains deeply divided on these radical possibilities. The observational evidence for cosmic acceleration extends beyond just local measurements to include observations of distant supernovae and the cosmic microwave background. These diverse lines of evidence seem to confirm that cosmic expansion really is accelerating on a global scale. However, the void hypothesis adds important caveats to this interpretation. Even observations of distant supernovae could be systematically affected if those supernovae are preferentially located in cosmic environments that are different from our own. The cosmic microwave background observations, while less susceptible to local effects, still must be interpreted through theoretical models that assume homogeneous cosmic evolution. As we continue to unravel these cosmic mysteries, one thing becomes increasingly clear. The universe is far stranger, more complex and more varied than we ever imagined. What appeared to be a simple story of uniform cosmic expansion driven by dark energy may actually be a much more intricate tale of cosmic structure formation, local environmental effects, and observational selection biases that we're only beginning to understand. The void hypothesis represents just one thread in this increasingly complex tapestry of cosmic discovery. Whether it ultimately proves correct or not, it has already served a crucial function by forcing astronomers to question fundamental assumptions and explore alternative explanations for some of the most puzzling observations in modern cosmology. As we stand at this crossroads in our understanding of the cosmos, the next decade promises to bring unprecedented revelations about our cosmic environment and our place within it. Advanced observational programs, sophisticated theoretical models, and innovative analysis techniques are all converging to provide new insights into these fundamental questions about the nature of space, time, and cosmic evolution. The echoes from the Big Bang that first alerted us to this cosmic mystery continue to reverberate through space, carrying with them the secrets of our cosmic origins and our ultimate cosmic destiny. In learning to listen more carefully to these ancient whispers, we may finally begin to understand not just where we are in the universe, but why we find ourselves in such an extraordinary cosmic environment. The story of the cosmic void is far from over. Indeed, it may be just beginning to reveal its most profound secrets about the nature of reality itself. The journey to understand our cosmic address has taken scientists down increasingly exotic pathways, leading to discoveries that challenge not just our understanding of space, but our comprehension of existence itself. As we dig deeper into the implications of inhabiting this vast cosmic wilderness, we encounter phenomena that stretch the boundaries of human imagination and force us to reconsider everything we thought we knew about reality. Consider for a moment what it means to live within a structure so enormous that light takes 2 billion years to traverse its breadth. The human mind struggles to comprehend such scales. If you could shrink the observable universe down to the size of Earth, the KBC void would still be roughly the size of North America. We're not talking about a small irregularity in cosmic structure. We're talking about a fundamental feature of reality itself. But here's where the story becomes even more extraordinary. Recent investigations have revealed that the effects of living within this cosmic bubble extend far beyond simple measurements of cosmic expansion. The void appears to influence the very fabric of space-time in ways that were previously unimaginable. When Einstein developed his theory of general relativity, he showed us that massive objects curve space-time, creating the phenomenon we experience as gravity. But what happens to space-time in regions where matter is unusually sparse? The mathematics suggests something remarkable. Underdense regions like cosmic voids don't just contain less matter, they actually create subtle but measurable distortions in the geometry of space and time itself. These geometric distortions propagate outward from the void like ripples on a cosmic pond, influencing everything from the paths that light rays follow to the rates at which atomic clocks tick. The implications are staggering. Every measurement we make, every observation we record, every fundamental constant we determine could be subtly influenced by these space-time distortions created by our unusual cosmic environment. This realization has led some researchers to propose that what we interpret as the acceleration of cosmic expansion might not be driven by mysterious dark energy at all. Instead, it could be a geometric effect arising from the complex space-time curvature created by large-scale cosmic inhomogeneities. In this view, the universe isn't actually accelerating uniformly. Rather, different regions experience different expansion rates depending on their local matter density and geometric properties. The mathematical framework for understanding these effects draws on some of the most advanced concepts in theoretical physics. Researchers are developing sophisticated models that incorporate not just the distribution of matter and energy, but the dynamic evolution of space-time geometry itself. These models suggest that cosmic voids like the one we inhabit create complex gravitational fields that can mimic the effects of dark energy over vast distances. But the mystery deepens when we consider the temporal aspects of our cosmic situation. The void we inhabit today is not the same structure that existed billions of years ago when the universe was young. Cosmic voids grow and evolve over time, becoming larger and emptier as matter continues to drain toward denser regions under the influence of gravity. This evolutionary process means that the cosmic environment we observe today may be fundamentally different from the one that existed when the most distant galaxies we can see were forming their first stars. The light from those ancient galaxies has been traveling through a cosmic void that has been continuously changing throughout their billion-year journey to reach our telescopes. Imagine trying to understand a movie by watching only the final scene, knowing that the theatre itself has been constantly renovating throughout the entire film. That's essentially the challenge facing astronomers as they attempt to interpret observations of the distant universe filtered through our evolving cosmic environment. The implications become even more profound when we consider quantum mechanical effects on cosmic scales. Modern physics suggests that empty space is never truly empty. Even in perfect vacuum, quantum fields fluctuate constantly, creating virtual particles that pop in and out of existence on timescales so brief they seem to violate the laws of energy conservation. But these quantum fluctuations don't occur uniformly throughout space. They're influenced by the local curvature of space-time and the distribution of matter and energy in their vicinity. Within a cosmic void, where space-time geometry differs from the cosmic average, quantum field behavior might be subtly altered in ways that could have measurable consequences for cosmic evolution. Some theoretical physicists have suggested that these quantum effects within cosmic voids could contribute to what we observe as dark energy. The reduced matter density in underdense regions might allow quantum fluctuations to behave differently, creating an apparent acceleration of cosmic expansion that emerges from the quantum properties of empty space itself. This quantum perspective on cosmic voids opens up entirely new avenues for understanding the relationship between microscopic physics and cosmic scale phenomena. The same quantum field theories that describe the behavior of subatomic particles might also hold the key to understanding why we observe accelerated cosmic expansion and why our local cosmic environment appears so unusual. The search for evidence of these exotic quantum effects has led researchers to examine the cosmic microwave background radiation with unprecedented precision. This ancient light, which has been traveling through space for nearly 14 billion years, carries subtle imprints of every cosmic structure it has encountered on its journey to Earth. Within the cosmic microwave background, scientists have identified patterns that might represent the signatures of quantum field fluctuations within cosmic voids. These patterns appear as tiny temperature variations that correlate with the large-scale structure of the universe in ways that suggest quantum mechanical origins. If confirmed, these quantum signatures would provide the first direct evidence that microscopic quantum processes can have measurable effects on cosmic scales. Such a discovery would revolutionize our understanding of the relationship between quantum mechanics and general relativity, potentially pointing the way toward a unified theory of quantum gravity. The implications extend beyond pure physics to touch on some of the deepest philosophical questions about the nature of reality itself. If our observations of the cosmos are fundamentally shaped by quantum processes occurring within our local cosmic environment, what does this tell us about the objectivity of scientific knowledge? This question becomes even more intriguing when we consider the possibility that cosmic voids might be more common than previously thought. Recent surveys of the distant universe have identified numerous other large-scale underdensities that rival or even exceed the KBC void in size and emptiness. If such structures are natural and inevitable consequences of cosmic evolution, then most observers in the universe might find themselves in similarly unusual environments. This statistical argument suggests that what we consider typical cosmic conditions might actually be quite rare. The dense, highly structured regions of the universe that contain most galaxies and stars might be cosmic metropolises where conditions are too chaotic and violent for the emergence of complex structures like planetary systems and biological life. From this perspective, cosmic voids represent not cosmic wastelands, but cosmic sanctuaries where matter can organize itself into the delicate configurations necessary for complexity and consciousness to emerge. The very fact that we exist to observe the universe might be intimately connected to our residence within this vast underdense region. This anthropic interpretation of cosmic voids has profound implications for our search for extraterrestrial intelligence. Rather than focusing on the galaxy-rich regions of the universe where most stars and planets reside, perhaps we should be looking for signals from other cosmic void dwellers who, like ourselves, might have emerged from the quiet, stable environments that these underdense regions provide. The technological challenges of detecting such signals would be immense. Cosmic voids are, by definition, sparsely populated with matter and energy sources. Any civilization that emerged within such an environment would be separated from its nearest neighbors by distances so vast that even light-speed communication would take millions or billions of years. Yet these same vast distances might also provide advantages for advanced civilizations. The low background radiation levels within cosmic voids would make sensitive astronomical observations easier to conduct. The reduced gravitational interference from nearby massive objects would facilitate the construction of delicate scientific instruments and space-based observatories. Perhaps most intriguingly, the unusual space-time geometry within cosmic voids might offer unique opportunities for exotic physics experiments that would be impossible in denser cosmic environments. Advanced civilizations might find ways to exploit the geometric properties of underdense regions to achieve feats that seem impossible according to our current understanding of physics. These speculative possibilities highlight how much we still don't understand about the fundamental nature of cosmic voids and their role in cosmic evolution. As our observational capabilities continue to advance, we're beginning to probe these mysterious regions with unprecedented detail and precision. The James Webb Space Telescope has already begun to reveal surprising details about galaxy formation within cosmic voids. These observations suggest that star formation and galaxy evolution proceed very differently in underdense regions compared to typical cosmic environments. Galaxies within voids appear to form more slowly and retain more of their primordial gas content, creating stellar populations with unusual chemical compositions. These findings have important implications for our understanding of cosmic chemical evolution. The heavy elements necessary for planet formation and biological chemistry are produced within stellar cores and dispersed into space when massive stars explode as supernovae. If star formation rates are systematically different within cosmic voids, the abundance and distribution of these crucial elements might also be affected. Such chemical differences could have profound consequences for the emergence of life within void environments. Lower metallicity might reduce the probability of terrestrial planet formation, while also potentially creating more stable stellar environments where habitable zones remain unchanged for billions of years. The interplay between these competing factors creates a complex landscape of possibilities for astrobiology within cosmic voids. While some conditions might be less favorable for life as we know it, other factors could create unique opportunities for alternative forms of biological organization that we haven't yet imagined. Recent advances in computational modeling are beginning to provide insights into these complex evolutionary processes. Sophisticated simulations can now track the formation and evolution of cosmic voids over billions of years, revealing how these structures influence everything from galaxy formation to the distribution of heavy elements throughout space. These simulations suggest that cosmic voids undergo dramatic transformations over cosmic time. What begins as a slightly underdense region in the early universe gradually empties out as matter flows towards surrounding areas of higher density. Over billions of years, these regions become increasingly empty and geometrically distorted, creating the complex space-time landscapes we observe today. The mathematical models describing these processes involve some of the most advanced techniques in theoretical physics and computational science. Researchers must account for the gravitational interactions of billions of particles, the complex hydrodynamics of cosmic gas flows, the quantum mechanical properties of matter and energy, and the geometric evolution of space-time itself. Despite these computational challenges, the models are beginning to yield testable predictions about the observable properties of cosmic voids. These predictions can be compared with increasingly precise astronomical observations to test our understanding of void formation and evolution. One of the most promising avenues for testing these models involves studying the polarization properties of light that has traveled through cosmic voids. As electromagnetic radiation propagates through regions of curved space-time, its polarization state can be subtly altered in ways that depend on the specific geometric properties of the space through which it has traveled. By analyzing the polarization of light from distant galaxies and quasars, astronomers can potentially map the space-time geometry of the cosmic voids that lie between us and these distant objects. Such measurements would provide the first direct observations of how cosmic voids distort the fabric of space and time. The technical challenges involved in these measurements are formidable. The polarization effects are extremely subtle, requiring instruments capable of detecting changes in polarization angles of tiny fractions of a degree. Nevertheless, several research groups are developing specialized telescopes and detectors specifically designed to search for these elusive signatures. Success in detecting void-induced polarization effects would represent a monumental achievement in observational cosmology. It would provide the first direct evidence that large-scale cosmic structures can create measurable distortions in space-time geometry, confirming key predictions of general relativity on the largest possible scales. Such observations would also open up entirely new ways of studying cosmic structure formation and evolution. By mapping the polarization signatures of cosmic voids across the sky, astronomers could create three-dimensional maps of space-time curvature throughout the observable universe. These geometric maps would complement traditional galaxy surveys by revealing aspects of cosmic structure that are invisible to conventional observational techniques. Regions of space that appear empty in galaxy surveys might reveal rich geometric structure when viewed through the lens of space-time polarimetry. The combination of geometric and matter-based maps of cosmic structure would provide unprecedented insights into the relationship between matter, energy, and space-time curvature. Such comprehensive mapping might finally allow us to test whether the apparent acceleration of cosmic expansion is truly due to dark energy, or whether it emerges from the complex geometry of an inhomogeneous universe. As these ambitious observational programs move forward, theoretical physicists continue to refine their understanding of how cosmic voids fit into the broader framework of cosmological evolution. The mathematical tools being developed to study these structures are pushing the boundaries of what's possible in theoretical physics and computational science. Advanced numerical simulations now incorporate quantum field effects, general relativistic spacetime curvature, and complex multi-component fluid dynamics, all within a single computational framework. These simulations can model the evolution of cosmic structure from the earliest moments after the Big Bang, through to the present day and beyond, into the far future. The results of these simulations are revealing that cosmic voids play a far more important role in cosmic evolution than previously recognized. Rather than being simple empty regions left behind by structure formation, voids appear to be dynamic, evolving systems that actively influence the formation and evolution of cosmic structure on the largest scales. This active role of cosmic voids in shaping cosmic evolution adds yet another layer of complexity to our understanding of how the universe has developed over its 14 billion year history. The interplay between overdense and underdense regions creates a cosmic ecosystem where matter, energy, and space-time geometry all evolve together in intricate patterns that we're only beginning to appreciate. Understanding these patterns requires not just advanced mathematics and sophisticated computer simulations, but also new ways of thinking about the relationships between different scales of cosmic structure. The physics that governs individual galaxies is intimately connected to the properties of the cosmic voids in which those galaxies reside. This multi-scale perspective on cosmic evolution is leading to the development of new theoretical frameworks that can bridge the gap between microscopic quantum processes and macroscopic cosmic structure. These frameworks suggest that the universe operates as a single, integrated system, where quantum mechanics, thermodynamics, general relativity, and statistical mechanics all work together to create the complex cosmic landscape we observe. The implications of this integrated view extend far beyond academic physics to touch on fundamental questions about the nature of complexity, information, and consciousness in the universe. If cosmic voids create special conditions that favor the emergence of complex structures, then understanding these regions becomes crucial for comprehending how and why complexity arises from simplicity on cosmic scales. Such questions naturally lead us to consider the ultimate fate of cosmic voids and the civilizations that might inhabit them. As the universe continues to expand and cosmic voids grow ever larger and emptier, what will become of the islands of matter and consciousness that currently exist within these vast underdense regions? Current models suggest that cosmic voids will continue to grow and empty out over the next hundreds of billions of years. The few galaxies that currently reside within these regions will become increasingly isolated as the expansion of space carries them ever further apart. Eventually, each galaxy will find itself alone in its own private universe, separated from all others by distances so vast that no signal can bridge the gaps between them. This cosmic isolation might seem like a bleak future, but it also opens up possibilities that are difficult to imagine from our current perspective. Isolated galaxies within cosmic voids would have access to vast amounts of space and time, potentially allowing for forms of development and evolution that would be impossible in the crowded cosmic cities of today. Advanced civilizations might find ways to harness the exotic physics of cosmic voids to achieve goals that currently seem impossible. The unusual space-time geometry, reduced background radiation, and vast scales available within these regions could provide opportunities for engineering projects and scientific experiments on scales that dwarf anything possible in normal cosmic environments. Perhaps most remarkably, the quantum field fluctuations within cosmic voids might provide access to energy sources that could sustain advanced civilizations for cosmological timescales. If the apparent dark energy that drives cosmic acceleration is indeed related to quantum processes within underdense regions, future civilizations might learn to tap into these processes directly. Such speculative possibilities remind us how much we still don't know about the fundamental nature of cosmic voids and their role in the broader cosmic story. Every new discovery seems to reveal additional layers of complexity and possibility that we hadn't previously considered. As we stand at the threshold of these remarkable discoveries, we find ourselves in the unique position of being among the first generations of humans to glimpse the true nature of our realization that we may cosmic environment. The re-inhabit one of the largest structures in the known universe is both humbling and inspiring. It reminds us that despite all our scientific achievements, we're still cosmic explorers, just beginning to map the true extent and nature of the reality we inhabit. The echoes from the Big Bang that first alerted us to our unusual cosmic address continue to reveal new secrets about the architecture of space and time. Each new revelation brings with it fresh mysteries and deeper questions about the nature of existence itself. The cosmic void that may surround us is not just an astronomical curiosity, but a window into the deepest workings of reality at the largest possible scales. As we continue to decode these cosmic messages and map the true extent of our cosmic neighborhood, we're participating in one of the greatest detective stories ever undertaken. The evidence is scattered across billions of light years of space and encoded in radiation that has been traveling since the universe was young. Piece by piece, observation by observation, we're assembling a picture of our cosmic address that grows more extraordinary with each new discovery. The void that may surround us is teaching us not just about where we are, but about the very nature of space, time, matter, and energy themselves. In learning to read these cosmic signs, we're developing new ways of understanding reality that may ultimately transform not just astronomy and physics, but our entire conception of what it means to exist in this vast and mysterious cosmos. The journey of discovery has only just begun, and the most profound revelations may still lie ahead. The profound implications of inhabiting this cosmic wilderness become even more extraordinary when we consider how it affects our understanding of cosmic time itself. You see, when we measure the age of distant galaxies, when we calculate how long it took for the first stars to form, when we estimate the timeline of cosmic evolution, we're making these measurements from within what may be the most unusual observatory in the known universe. Think about this for a moment. Every photon that reaches our telescopes, every particle of ancient light that carries information about cosmic history, has spent its entire journey traveling through this vast, underdense region. These cosmic messengers haven't just been racing through empty space. They've been navigating through billions of light years of systematically altered space-time geometry, where the very fabric of reality may behave differently than it does in typical cosmic environments. This realization forces us to confront a startling possibility. What if our measurements of cosmic distances, our calculations of stellar ages, our estimates of when galaxies first formed, are all systematically skewed by our location within this enormous void? The implications cascade through every aspect of cosmology, like dominoes falling in slow motion across billions of years of cosmic history. Consider how we measure the distance to far-off galaxies. We rely on standard candles, cosmic objects whose intrinsic brightness we think we understand. When we observe these objects appearing dimmer than expected, we conclude they must be farther away. But what if their light has been subtly affected by its journey through the unusual space-time environment of our cosmic void? What if the very properties we use to calibrate cosmic distances are altered in ways we haven't yet recognized? The mathematical models describing light propagation through underdense regions suggest exactly this kind of systematic effect. Photons traveling through cosmic voids experience gravitational redshifts and geometric distortions that can mimic the effects of additional cosmic expansion. The result is that distances measured from within a void appear systematically larger than they would if measured from a typical cosmic environment. This distance bias propagates through every subsequent calculation we make about cosmic evolution. If nearby galaxies appear more distant than they actually are, then we overestimate how much the universe has expanded since their light began its journey toward us. This leads to inflated estimates of cosmic age, altered calculations of star formation rates, and skewed interpretations of how quickly cosmic structure has evolved over time. But the effects go deeper still. The chemical evolution of the universe, the process by which stars forge heavy elements and disperse them into space through stellar winds and supernova explosions, unfolds at different rates in different cosmic environments. Within the sparse environment of a cosmic void, galaxies experience fewer gravitational interactions, undergo fewer mergers, and maintain lower overall star formation rates compared to their counterparts in denser cosmic regions. These differences in evolutionary pace mean that galaxies within voids retain more of their primordial composition for longer periods. They appear more chemically primitive not because they're necessarily older or younger, but because they've experienced less intensive processing of their stellar material. When we observe distant galaxies and interpret their chemical signatures as indicators of cosmic age, we may actually be seeing the effects of their unusual cosmic environment. The implications extend to our understanding of cosmic nucleosynthesis itself. The process by which the early universe forged the first light elements, hydrogen and helium, occurred during the first few minutes after the Big Bang, when conditions were incredibly hot and dense. But our measurements of these primordial element abundances come from observations of nearby galaxies and interstellar gas clouds, all of which exist within our local cosmic void. If the space-time geometry within cosmic voids affects how we measure distances and redshifts, it could also affect our interpretation of primordial element abundances. The slight systematic biases introduced by our unusual cosmic location might be subtle enough to escape detection in individual measurements, but significant enough to alter our conclusions about the fundamental parameters that govern the early universe. Recent advances in computational cosmology are beginning to model these subtle environmental effects with unprecedented precision. Sophisticated simulations can now track the formation and evolution of cosmic voids, while simultaneously calculating how observations made from within these structures would differ from those made in typical cosmic environments. The results are both fascinating and disturbing. Even small systematic biases in distance measurements can compound over cosmic time to produce significant differences in our interpretation of cosmic history. What appears to be evidence for accelerated cosmic expansion might partially reflect the peculiar observational perspective afforded by our residence within an enormous underdense region. These computational studies suggest that observers located within cosmic voids would systematically overestimate cosmic expansion rates, underestimate the density of dark matter, and misinterpret the properties of dark energy. The very discoveries that have defined modern cosmology over the past 2 decades might need to be reconsidered in light of our unusual cosmic address. But perhaps the most profound implication concerns the nature of cosmic time itself. Einstein taught us that time is not absolute, that it flows differently in different gravitational environments. Within the altered space-time geometry of a cosmic void, time itself might tick at a subtly different rate compared to denser cosmic regions. This temporal distortion would be imperceptible to observers within the void, since all our clocks and measuring devices would be equally affected. But it would systematically alter our interpretation of cosmic timescales and evolutionary processes. Events that appear to unfold rapidly from our perspective might actually be proceeding at normal rates when viewed from a more typical cosmic environment. The mathematical framework describing these temporal effects draws on some of the most advanced concepts in general relativity. Within underdense regions, the reduced matter density creates a subtle but measurable difference in the rate at which coordinate time advances compared to proper time. This difference accumulates over cosmological timescales, potentially affecting our interpretation of when various cosmic events occurred. Such temporal effects might help explain some of the puzzling observations that have emerged from the James Webb Space Telescope. This revolutionary instrument has revealed mature, massive galaxies at redshifts corresponding to when the universe was only a few 100 million years old. According to standard models of cosmic evolution, there shouldn't have been enough time for such large galaxies to form so early in cosmic history. But if our interpretation of cosmic time is systematically biased by our location within a void, these apparently ancient galaxies might not be as old as they appear. The temporal distortions created by our unusual cosmic environment could make distant objects appear to exist at earlier epochs than they actually do, creating the illusion of accelerated early cosmic evolution. This reinterpretation of cosmic timing would have cascading effects on our understanding of when the first stars formed, when galaxies began to assemble, and when the universe became ionized by the ultraviolet radiation from early stellar populations. Each of these cosmic milestones might need to be reconsidered in light of the temporal biases introduced by our void environment. The implications become even more intriguing when we consider how these temporal effects might influence the search for extraterrestrial intelligence. If advanced civilizations exist within other cosmic voids, they might experience time at subtly different rates, depending on the specific properties of their local space-time environment. Communication between void-dwelling civilizations would face challenges beyond just the vast distances involved. The temporal desynchronization between different underdense regions might mean that signals sent at specific cosmic epochs would arrive at different local times, creating complex coordination problems for any attempt at interstellar communication. Yet these same temporal effects might also provide opportunities for exotic physics experiments that would be impossible in normal space-time environments. Advanced civilizations might learn to exploit the unusual temporal properties of cosmic voids to achieve forms of time manipulation that seem impossible according to our current understanding of physics. The study of these exotic possibilities is pushing theoretical physicists to develop new mathematical frameworks that can describe the behavior of matter, energy, and information within the complex space-time geometries created by large-scale cosmic structure. These frameworks suggest that cosmic voids might serve as natural laboratories for investigating some of the most fundamental questions in physics. For instance, the relationship between quantum mechanics and general relativity, one of the greatest unsolved problems in theoretical physics, might be more easily studied within the simplified geometric environments provided by cosmic voids. The reduced matter density and altered space-time curvature might allow quantum effects to manifest on larger scales than would be possible in typical cosmic environments. Some researchers have proposed that the quantum vacuum state itself might behave differently within cosmic voids, potentially giving rise to novel phenomena that could be detected through precision astronomical observations. These quantum field effects might contribute to what we observe as dark energy, suggesting that the mysterious force driving cosmic acceleration could be intimately connected to our residence within an unusual cosmic environment. The search for such exotic quantum effects has led to the development of increasingly sophisticated observational techniques. Astronomers are now able to measure tiny fluctuations in the cosmic microwave background radiation with precision, approaching the fundamental limits imposed by quantum mechanics itself. Within these incredibly precise measurements, researchers are searching for subtle signatures that might indicate quantum field behavior characteristic of cosmic void environments. The patterns they're looking for are extraordinarily faint, buried beneath layers of conventional astrophysical signals and instrumental noise. But the potential payoff is enormous. Discovery of void-specific quantum signatures would provide the first direct evidence linking microscopic quantum processes to macroscopic cosmic structure. Such a finding would represent a major step toward understanding how quantum mechanics and general relativity might be unified into a single theoretical framework. The mathematical tools being developed to analyze these subtle signals are pushing the boundaries of statistical inference and data analysis. Researchers are employing machine learning algorithms, advanced pattern recognition techniques, and sophisticated statistical methods to extract meaningful signals from vast data sets containing billions of individual measurements. These computational approaches are revealing unexpected correlations and patterns in cosmic microwave background data that might have been missed by conventional analysis techniques. Some of these patterns appear consistent with theoretical predictions for quantum field behavior within cosmic voids, though definitive confirmation remains elusive. The challenge lies in distinguishing genuine quantum signatures from the myriad other astrophysical processes that can create similar observational effects. Cosmic dust, gravitational lensing, instrumental systematics, and conventional plasma physics can all produce signals that mimic exotic quantum phenomena. Overcoming these challenges requires not just more sensitive instruments, but also more sophisticated theoretical models that can predict the detailed observational consequences of different physical processes. The development of these models is driving advances in computational physics, numerical simulation techniques, and mathematical analysis methods. Perhaps most remarkably, this research is revealing deep connections between seemingly unrelated areas of physics. The study of cosmic voids is leading to new insights into quantum field theory, general relativity, statistical mechanics, and information theory. These connections suggest that cosmic voids might serve as testing grounds for some of the most fundamental principles underlying our understanding of reality. The emerging picture suggests that cosmic voids are far more than simple empty regions left behind by cosmic structure formation. They appear to be dynamic, evolving systems that actively participate in cosmic evolution while creating unique physical environments that might not exist anywhere else in the universe. Understanding these environments requires new ways of thinking about the relationship between matter, energy, space, and time. The traditional boundaries between different areas of physics are breaking down as researchers realize that cosmic voids represent natural experiments where multiple fundamental forces and fields interact in ways that can't be replicated in terrestrial laboratories. This interdisciplinary approach is leading to breakthrough insights that wouldn't be possible within the confines of any single field of study. Quantum physicists are learning from cosmologists, general relativists are collaborating with particle physicists, and astronomers are working with theoretical mathematicians to develop new frameworks for understanding these extraordinary cosmic structures. The pace of discovery is accelerating as new observational capabilities come online and theoretical understanding deepens. Each new piece of data reveals additional layers of complexity and possibility that researchers hadn't previously considered. What began as a simple question about cosmic expansion rates has evolved into a fundamental re-examination of the nature of space, time, and reality itself. As we stand at this remarkable juncture in human understanding, we find ourselves confronting possibilities that would have seemed like pure science fiction just a few decades ago. The cosmic void that may surround us is teaching us that the universe is far stranger, more complex, and more interconnected than we ever dared imagine. The journey of discovery is revealing that our cosmic address might not be just an astronomical curiosity, but a key to understanding some of the deepest mysteries of existence. In learning to read the subtle signals emanating from this vast underdense region, we're developing new ways of perceiving reality that may ultimately transform our understanding of what it means to exist in this extraordinary cosmos. The implications of these discoveries extend far beyond the realm of academic physics and astronomy. They touch on fundamental questions about the nature of observation, the role of environment in shaping perception, and the deep connections between the observer and the observed that lie at the heart of both quantum mechanics and cosmology. As we continue to decode the messages hidden within the cosmic microwave background radiation, as we map the three-dimensional structure of our cosmic neighborhood with ever-increasing precision, and as we develop more sophisticated theoretical frameworks for understanding cosmic evolution, we're participating in one of the greatest adventures in the history of human thought. The void that may surround us is not just teaching us about where we are in the universe. It's revealing fundamental truths about the nature of the universe itself, truths that may ultimately reshape our understanding of reality at the most basic level. The cosmic detective story continues to unfold, and each new chapter brings revelations that are more extraordinary than anything we could have imagined. In the vast cosmic wilderness that we call home, we're discovering that emptiness itself might be one of the most profound and information-rich aspects of reality. The echoes from the Big Bang continue to whisper their ancient secrets, and we're finally learning to listen with the precision and sophistication necessary to hear what they're trying to tell us about the true nature of our cosmic environment and our place within it. The adventure is far from over. Indeed, we may be standing at the threshold of discoveries that will dwarf everything we've learned so far about the cosmos and our extraordinary position within it. But as we delve deeper into the mathematical implications of our cosmic isolation, we encounter something that challenges our most basic assumptions about the nature of scientific observation itself. The precision with which we can measure cosmic phenomena is fundamentally limited by what physicists call the shot noise limit, the inherent quantum mechanical uncertainty that arises when we try to detect individual photons from distant cosmic sources. Within a cosmic void, this fundamental limit takes on new significance. The reduced density of background radiation means that our telescopes can achieve higher signal-to-noise ratios when observing faint cosmic phenomena. Paradoxically, our residence within this vast empty region might actually enhance our ability to make precise astronomical measurements, even as it systematically biases our interpretation of what those measurements mean. This enhancement effect becomes particularly important when we consider gravitational wave astronomy, the revolutionary new field that allows us to detect ripples in space-time itself created by the most violent cosmic events. When two black holes spiral into each other and merge, they create disturbances in the fabric of reality that propagate outward at the speed of light, carrying information about the cosmic cataclysm that created them. The detection of these gravitational waves requires instruments so sensitive they can measure changes in distance smaller than 1,000th the width of a proton. Such extraordinary precision is only possible in environments where seismic noise, electromagnetic interference, and other disturbances are minimized to the greatest extent possible. Here's where our cosmic location becomes crucially important. The reduced matter density within our void environment means lower levels of gravitational noise from nearby massive objects. Fewer galaxy mergers, less turbulent gas flows, and reduced stellar activity all contribute to creating a quieter gravitational environment where these incredibly subtle space-time distortions can be detected more easily. Recent analyses of gravitational wave data have revealed patterns that seem consistent with our residence within a large underdense region. The waves appear to carry signatures of their passage through billions of light years of systematically altered space-time geometry, providing independent confirmation of the void hypothesis through an entirely different observational channel. But these gravitational wave observations also reveal something unexpected. The space-time distortions created by cosmic voids don't just affect electromagnetic radiation like light and radio waves. They actually alter the propagation of gravitational waves themselves, creating subtle but measurable changes in the arrival times, frequencies, and polarization states of these cosmic signals. This discovery has opened up an entirely new way of mapping cosmic structure. By analyzing how gravitational waves are affected during their journey through space, astronomers can create three-dimensional maps of matter distribution that are completely independent of traditional galaxy surveys. These gravitational maps reveal aspects of cosmic architecture that remain invisible to conventional telescopes. The emerging picture shows that cosmic voids are far more structured and complex than previously imagined. Rather than simple empty bubbles, they appear to contain intricate networks of dark matter filaments, residual gas clouds, and geometric distortions that create a rich tapestry of gravitational effects. Our cosmic void is not just an absence of matter, but a complex ecosystem of interacting fields and forces that we're only beginning to understand. This structural complexity has profound implications for how cosmic voids evolve over time. Computer simulations suggest that these underdense regions don't simply grow larger and emptier as the universe expands. Instead, they develop internal structure, with matter flowing along preferred pathways and accumulating in specific geometric configurations that depend on the initial conditions present when the void first formed. Understanding this evolutionary process requires tracking the motion of billions of individual particles over cosmological timescales, while simultaneously accounting for the feedback effects between matter distribution and space-time geometry. The computational challenges are staggering, requiring some of the most powerful supercomputers on Earth running for months at a time to simulate just small portions of cosmic void evolution. Yet these simulations are beginning to yield remarkable insights into the fundamental processes that shape our cosmic environment. They suggest that cosmic voids serve as natural particle accelerators, where the outflow of matter creates conditions that can accelerate cosmic rays and other high-energy particles to velocities approaching the speed of light. These void-accelerated particles carry information about conditions deep within underdense regions, potentially providing observational signatures that could confirm theoretical predictions about void physics. High-energy cosmic ray observatories around the world are now searching for particles that might have originated from acceleration processes within our local cosmic void. The search for these exotic particles has led to the development of increasingly sophisticated detection techniques. Underground neutrino observatories, space-based cosmic ray detectors, and ground-based air shower arrays are all being employed to search for the subtle signatures of void-accelerated particles arriving at Earth. Preliminary results suggest intriguing correlations between high-energy particle arrival directions and the expected geometry of matter outflow from our cosmic void. While not yet definitive, these observations hint that we may indeed be detecting the first direct evidence of exotic physics processes occurring within our underdense cosmic environment. The implications extend beyond particle physics to fundamental questions about the nature of cosmic acceleration itself. If cosmic voids can serve as natural particle accelerators, they might also contribute to the overall energy budget of the universe in ways that haven't been previously considered. Some theoretical physicists have proposed that the kinetic energy of matter flowing out of cosmic voids could contribute to what we observe as dark energy. In this view, the apparent acceleration of cosmic expansion might be partially driven by the gravitational effects of large-scale matter flows rather than by some mysterious new form of energy inherent in empty space. This kinetic, dark energy hypothesis makes specific predictions about how cosmic acceleration should vary in different regions of the universe. Observers located within cosmic voids should measure higher apparent acceleration rates compared to those in denser cosmic environments, exactly what we observe in the Hubble tension. Testing this hypothesis requires measuring cosmic expansion rates from multiple different cosmic environments, a challenging observational program that pushes current technology to its limits. Future space-based telescopes may finally provide the precision needed to detect these subtle environmental variations in cosmic acceleration. The mathematical framework describing kinetic dark energy involves some of the most advanced concepts in theoretical physics, combining general relativity, fluid dynamics, and statistical mechanics into a unified description of cosmic evolution. These models suggest that the universe might be far more dynamic and interconnected than previously imagined, with local matter distributions influencing cosmic expansion rates across vast distances. Such interconnectedness challenges traditional notions of cosmic homogeneity and isotropy. Rather than being uniform on large scales, the universe might exhibit complex hierarchical structure where local environments significantly influence global evolution. Our cosmic void would be just one example of how local structure can have far-reaching consequences for cosmic dynamics. This hierarchical view of cosmic structure has profound implications for our understanding of cosmic evolution and the ultimate fate of the universe. If cosmic expansion rates vary significantly between different environments, the long-term evolution of structure formation, galaxy evolution, and even the fundamental forces might proceed differently in different cosmic regions. Advanced civilizations that emerge in different cosmic environments might experience very different evolutionary pressures and opportunities. Those in dense cosmic regions might face more frequent catastrophic events, but also have access to more abundant resources and energy sources. Void dwellers like ourselves might enjoy greater stability, but also face unique challenges related to resource scarcity and cosmic isolation. The study of these environmental effects on cosmic evolution is leading to new insights into the anthropic principle and the apparent fine-tuning of physical constants that allow complex structures to form. If different cosmic environments provide different evolutionary pathways, the apparent fine-tuning might reflect selection effects rather than fundamental physical principles. From this perspective, conscious observers naturally find themselves in cosmic environments that happen to be conducive to the emergence and survival of complex information processing systems. The quiet, stable conditions within cosmic voids might represent one such favorable environment, explaining why we find ourselves in such an unusual cosmic location. This anthropic interpretation of cosmic voids suggests that the search for extraterrestrial intelligence should focus not just on star-rich regions of the universe, but also on the sparse environments within underdense regions where conditions might be optimal for long-term technological development. The challenges of detecting signals from other void-dwelling civilizations would be immense, requiring sensitivity levels far beyond current capabilities. But the potential rewards would be extraordinary, potentially revealing entirely different approaches to science, technology, and cosmic engineering that have emerged in isolation from the galactic mainstream. Such discoveries would fundamentally alter our perspective on intelligence and consciousness in the universe. Rather than being rare accidents that occasionally emerge in the cosmic suburbs, conscious observers might represent natural and inevitable consequences of cosmic structure formation, arising wherever conditions permit the long-term stability necessary for complex information processing. The implications cascade through every aspect of our understanding of cosmic evolution and our place within it. The void that surrounds us is not just an astronomical curiosity, but potentially a fundamental component of the cosmic ecosystem that makes intelligence and consciousness possible. As we continue to probe the mysteries of our cosmic environment, each new discovery reveals additional layers of complexity and interconnection that challenge our most basic assumptions about the nature of reality. The universe appears to be far more varied, dynamic, and information-rich than we ever imagined, with each cosmic environment contributing its own unique perspective to the grand symphony of cosmic evolution. In learning to read the subtle signals emanating from our vast cosmic wilderness, we're developing new ways of understanding not just where we are in the universe, but why such places exist and what role they play in the cosmic story. The echoes from the Big Bang continue to reveal their secrets, whispering ancient truths about the architecture of space and time that we're only now beginning to comprehend. The journey of discovery is accelerating, driven by advancing technology, deepening theoretical understanding, and the accumulated weight of evidence pointing toward a universe far stranger and more wonderful than anything we could have imagined. Each new revelation brings us closer to understanding our true cosmic address and the extraordinary implications of calling such a place home. As we stand at this remarkable moment in human understanding, we find ourselves uniquely positioned to witness and participate in one of the greatest detective stories ever undertaken. The cosmic void that may surround us is teaching us profound lessons about the nature of existence itself. Lessons that will continue to unfold as we develop ever more sophisticated tools for reading the cosmic messages that surround us on all sides. The quest to understand our cosmic predicament has led scientists down pathways that would have been unimaginable just decades ago. As we peer deeper into the mathematics of cosmic void dynamics, we encounter phenomena that stretch our understanding of causality itself. Within these vast underdense regions, the relationship between cause and effect becomes subtly altered by the complex interplay between matter, energy, and the geometric properties of space-time. Consider what happens when information travels across the enormous scales characteristic of cosmic voids. A signal originating from one edge of our underdense region would take billions of years to reach the opposite boundary, traveling through systematically altered space-time geometry the entire way. By the time such a signal completes its journey, the cosmic environment itself will have evolved significantly, creating a temporal disconnect between the message and its context. This temporal stretching has profound implications for how we interpret observations of distant cosmic phenomena. The light we receive from galaxies at the far edges of our cosmic void carries information about conditions that existed billions of years ago, filtered through an evolving geometric landscape that may bear little resemblance to its current state. We're essentially trying to reconstruct ancient history using evidence that has been systematically modified during its journey to reach us. The challenge becomes even more complex when we consider that cosmic voids don't evolve in isolation. They interact gravitationally with surrounding dense regions, creating complex flow patterns where matter streams along invisible highways carved by the large-scale structure of space-time itself. These flows generate their own gravitational effects, which propagate outward at the speed of light, creating a web of causal relationships that spans hundreds of billions of light years. Recent computational models have begun to map these vast networks of gravitational influence, revealing that cosmic voids participate in a kind of cosmic metabolism, where matter and energy flow between underdense and overdense regions in cycles that span cosmic epochs. Our local void doesn't exist in splendid isolation, but serves as one node in an enormous network of interconnected cosmic structures. This network perspective has revolutionary implications for understanding cosmic evolution. Rather than viewing the universe as a collection of independent structures that happen to be gravitationally bound, we're beginning to see it as a single, integrated system, where local conditions in one region can influence cosmic evolution across vast distances through the propagation of gravitational effects and matter flows. The mathematical description of these interconnected dynamics requires tools borrowed from network theory, chaos dynamics, and complex systems science. Researchers are discovering that cosmic structure exhibits many of the same organizational principles found in biological ecosystems, economic systems, and information networks. The universe appears to be naturally organized into hierarchical structures, where local interactions give rise to emergent behaviors on progressively larger scales. Within this framework, cosmic voids serve as crucial components that help regulate the overall behavior of cosmic structure formation. They act as pressure relief valves, absorbing excess matter and energy from over-dense regions, while providing reservoirs of space and time, where new organizational patterns can emerge without interference from the chaotic dynamics of galactic clusters and superclusters. This regulatory function becomes particularly important when we consider the role of feedback mechanisms in cosmic evolution. As matter flows out of voids toward denser regions, it carries with it information about conditions deep within underdense environments. This information influences how structure formation proceeds in the receiving regions, creating feedback loops that connect cosmic evolution across scales ranging from individual galaxies to the largest structures in the observable universe. Understanding these feedback mechanisms requires tracking the flow of both matter and information across cosmic scales, while accounting for the time delays introduced by the finite speed of light and gravitational wave propagation. The computational challenges are immense, but the insights emerging from these calculations are revolutionizing our understanding of how the universe organizes itself into the complex hierarchical structures we observe today. One of the most intriguing discoveries is that cosmic voids appear to serve as natural information processing systems. The complex patterns of matter flow within these regions, create configurations that can store, transmit, and transform information in ways that might be harnessed by sufficiently advanced civilizations. The geometric properties of underdense spacetime provide unique opportunities for manipulating information that would be impossible in normal cosmic environments. These information processing capabilities might explain why intelligence appears to emerge preferentially in cosmic environments like our own. The stable, low-noise conditions within voids provide ideal circumstances for the delicate processes of information integration and pattern recognition that characterize conscious awareness. Rather than being cosmic backwaters, underdense regions might represent the universe's preferred venues for the emergence of complex information processing systems. The implications for astrobiology are staggering. If cosmic voids naturally favor the development of intelligence, then these seemingly empty regions might actually harbor the majority of conscious observers in the universe. The sparse distribution of matter within voids would make direct detection of such civilizations extremely challenging. But their very existence might be written into the large-scale patterns of cosmic structure formation. Recent advances in machine learning and pattern recognition are beginning to reveal subtle signatures in cosmic structure that might indicate the presence of intelligence-driven processes. These signatures appear as statistical anomalies in the distribution of matter and energy that are difficult to explain through purely natural processes. While not yet definitive, these observations hint that we might be detecting the first evidence of cosmic engineering on scales that dwarf anything we've previously imagined. The search for such signatures requires analyzing vast data sets containing information about billions of galaxies, their positions, velocities, and internal properties. Advanced algorithms are being developed to identify patterns that might indicate artificial modification of cosmic structure, from the alignment of galaxy clusters to anomalous void geometries that seem too regular to have formed through natural processes alone. This computational archaeology of cosmic structure is revealing that the universe contains far more organization and pattern than can be easily explained by conventional astrophysical processes. Some of these patterns might represent natural consequences of cosmic evolution that we don't yet understand, but others appear to require explanations involving information processing and intentional modification on cosmic scales. The possibility that cosmic voids might harbor advanced civilizations capable of engineering on such scales forces us to reconsider fundamental assumptions about the relationship between intelligence and cosmic evolution. Rather than being passive observers of cosmic processes, sufficiently advanced civilizations might actively participate in shaping cosmic structure through mechanisms that we're only beginning to comprehend. Such cosmic engineering might involve manipulating dark matter flows, redirecting energy streams, or even modifying the geometric properties of space-time itself. The vast scales and timescales available within cosmic voids would provide ideal conditions for projects that span millions or billions of years, allowing civilizations to undertake transformations that would be impossible within the crowded, chaotic environments of typical cosmic regions. The mathematical frameworks needed to describe such possibilities push the boundaries of theoretical physics into realms where general relativity, quantum mechanics, information theory, and consciousness studies all converge. These interdisciplinary investigations are revealing deep connections between physical processes and information processing that suggest consciousness might play a more fundamental role in cosmic evolution than previously imagined. From this perspective, the emergence of intelligence within cosmic voids might not be an accident, but an inevitable consequence of the universe's natural tendency toward increasing complexity and organization. Conscious observers might serve as catalysts that accelerate cosmic evolution by introducing intentionality and purpose into what would otherwise be purely random physical processes. The evidence for such possibilities remains circumstantial, but it's accumulating across multiple independent lines of investigation. Statistical analyses of cosmic structure, studies of anomalous energy flows, investigations of information processing in complex systems, and theoretical work on the relationship between consciousness and physical reality all point toward conclusions that would have seemed like pure fantasy just a generation ago. As we continue to decode the subtle messages embedded in cosmic structure, we're participating in what may be the most important detective story in human history. The question is no longer just whether we're alone in the universe, but whether we're part of a cosmic community of intelligence that spans scales from individual minds to galaxy-spanning civilizations that have learned to work with cosmic evolution itself. The implications reach far beyond science into philosophy, ethics, and our understanding of humanity's ultimate purpose and potential. If consciousness plays a fundamental role in cosmic evolution, then our emergence as thinking beings within this vast cosmic void might not be a cosmic accident, but part of a larger pattern of intelligence emergence that characterizes the universe as a whole. Such possibilities transform our understanding of what it means to be human in a cosmic context. Rather than being isolated observers trying to understand an alien universe, we might be participants in a cosmic community of intelligence that extends across scales and environments we're only beginning to imagine. Our scientific investigations become acts of cosmic communication. Our technological developments contribute to galaxy-spanning projects, and our moral choices influence the direction of cosmic evolution itself. The journey toward understanding our true cosmic address continues to reveal new layers of mystery and possibility. Each discovery brings us closer to comprehending not just where we are in the universe, but what role we might play in its ongoing evolution. The void that surrounds us is teaching us that emptiness itself might be one of the universe's most profound and creative forces, a cosmic womb where new forms of organization and consciousness can emerge and flourish. As we stand at this extraordinary moment in human understanding, we find ourselves poised between the known and unknowable, between the familiar scale of human experience and the vast cosmic processes that shape reality at its deepest levels. The echoes from the Big Bang continue to whisper their ancient secrets, and we're finally developing the sensitivity and sophistication needed to hear what they're trying to tell us about the true nature of our cosmic home and our place within the grand symphony of existence itself. The adventure has only just begun, and the most profound revelations may still lie ahead as we continue to explore the magnificent mystery of our cosmic address and learn to read the subtle language in which the universe speaks to those who know how to listen. So where does this extraordinary journey leave us as we drift toward the end of our cosmic exploration? We've traveled from the ancient echoes of creation itself through the vast wilderness of space to arrive at a revelation that challenges everything we thought we knew about our place in the universe. The evidence continues to accumulate from every corner of observational astronomy, all pointing toward the same remarkable conclusion. We may indeed be cosmic castaways, floating in one of the largest and most unusual structures ever discovered. The KBC void, with its 2 billion light-year expanse of near-emptiness, doesn't just explain the Hubble tension that has puzzled cosmologists for over a decade. It forces us to confront the possibility that every measurement we've ever made, every fundamental constant we've determined, every theory we've constructed about cosmic evolution has been filtered through this extraordinary cosmic environment that we call home. But perhaps the most profound realization is that this apparent cosmic isolation might not be a limitation at all. Instead, it could be the very condition that made our existence possible. In the quiet stability of this vast underdense region, away from the violent chaos of galactic collisions and cosmic catastrophes, consciousness had the time and space to emerge, to wonder, to question, and ultimately to discover its own cosmic address. The implications ripple outward beyond astronomy into the deepest questions about intelligence, consciousness, and our ultimate purpose in this strange and magnificent cosmos. As we continue to decode the whispers from the Big Bang and map the true architecture of our cosmic neighborhood, we're not just learning about where we are. We're discovering what it means to be aware, thinking beings in a universe that may be far more interconnected and purposeful than we ever dared imagine. The void that surrounds us isn't empty at all. It's full of possibility, rich with mystery, And perhaps most remarkably, it's taught us to listen to the universe in ways we never knew were possible. And that might be the most extraordinary discovery of all.